It's all
Okay, let's begin the class. There is I noticed I was working on your final project guideline, whatever. I noticed there was a problem with the syllabus, the grading criteria in the syllabus. So I just have to change a little bit the grading criteria. So this is the updated grading criteria. Homework is worth 15 points, 5 points each homework. Exams are going to be worth 60% total, 2 exams, which hasn't changed. Final project, and the syllabus it says 30%, which was the case last year when the students had a final report and a presentation. We don't have a presentation anymore, so it's going to be 25%, which will bring the total to 100%. So, and the attendance quizzes are going to be just a bonus. So if you have attended the class 5 times, you will receive 5%. Too many bonuses. But, I mean, there's a limit on how much I can change the grading criteria at the end of the semester, right? I didn't want to give this too many bonuses, but yeah. The rest of it hasn't changed. Course evaluation bonus is 2%, as it has been the case. And I mean, you know about the homework bonuses and the exam uploads, which will give you, can add a total of 6% to your grade, final grade. So essentially just showing up and submitting a copy of your exam on Blackboard will give you 11 points. You don't even need to know any propulsion to receive 11 points. I guess also submit the course evaluation, 13 points. Just doing all of these things will bump your letter grade, at least 1 letter grade, right? Yeah. Do we have any questions? Yes.
So, have you posted the videos for answers yet? Or
no, I haven't posted. I will post the guideline for the project today, right? Later, so like during the night when I get home, and I will work on the videos hopefully throughout the week, upload them. The reason I haven't worked on the videos is because I fell ill last weekend, and really we're dealing with a lot of deadlines, so sorry about it, but I will upload it. And after the propulsion exam, we have 2 more lectures. We will just I'll try to reserve the computer labs. If they're free, we're going to go to the computer labs and work on the project together. These are the last 2 lectures of the class. We can also, we don't really have any real lectures for orbital mechanics as well. We can also use the time that is supposed to be orbital mechanics for this project. So we can have like 4-hour sessions for propulsion. Questions? So the grading criteria has changed a little bit, and yeah, I guess I have to check the criteria for the orbital mechanics as well to make sure that one is listed correctly. Again, this is the updated, and I am recording this lecture partly because of this updated grading criteria. So those of you who are not in class won't be able to complain as well, right? And I did also receive a request from one of the students who is sick today to record the lecture and post it on Blackboard. So the point is, if you are sick, don't come to class. Right? I will do whatever you need to catch up. Just don't come to class, okay? If you have a sickness that I can get, like if it's a viral sickness, right? Okay. That doesn't really apply to mental sickness. But not that I'm not implying anything. It was just a very, very, I guess, bad joke. And I hope all of you have voted yesterday, at least. I did vote yesterday, last minute. And yeah. I hope if you are a Trump supporter, you're happy with the results. And if you're not a Trump supporter, next time, hopefully. Yeah. Okay, let's talk about electric propulsion. So, alternative modes of propulsion. That most of it will be spent on electric propulsion. So today we are going to talk about principles of electrical propulsion, which essentially means that we are going to talk a little bit about the basics of electronics, physics, electronics, like electric field, magnetic field, and how much of the force that those fields can generate, right? And we're going to move on to electrothermal thrusters, specifically talk about electrothermal thrusters, and we're going to move on to electrostatic thrusters. I think the electrostatic ones, and electromagnetic, and the nuclear rocket and solar rockets, we will discuss on Monday. I don't think we're going to have enough time to get to all of these today. But essentially, solar rockets are the last thing we are going to discuss. And the only real calculations and equations you're going to see are going to be in the first three parts of the lecture. The rest of it is just an introduction, essentially. The reason is there will be higher level electronics involved in those calculations, as plasma physics calculations. So we need to have graduate level understanding of plasma discharge. So, yeah, so the calculations for this is going to be somewhat easier than the rest of the course, which is, I guess, something that I keep saying, right? Okay, so why do we move to alternative modes of propulsion? Like, what are the limitations of chemical rockets? Chemical rocket, designing a chemical rocket is pretty simple. Just have to have a shell, right, put some fuel in it, and set it on fire, right, and go forward. That's the idea of a chemical rocket. But they have some fundamental limitations. Who can tell me what their limitations are? Yes.
The two biggest are like all combustion reactions are going to have like maximum efficiency that you're running into. And if you're talking about like propellantless alternative propulsion with chemical rockets, you have to carry the propellant.
Yes, so that is also true for all. I mean, you have to carry your propellants always, right?
Solar cells. But
yeah. Any other opinions other than the weight problem? Yes.
You're gonna have like a constant like changing weight, like you're gonna be like heavier, and then like you have to account for it like getting lost over time.
I guess that's a good point. Yeah. What else?
They're more efficient for like trajectory changes, where because if you're burning a chemical rocket, your specific impulse is going to be really low, and you just have a lot of force really fast. But electric propulsion has really high specific impulses, so that you can have a thrust force for a longer period of time.
That is, yes, that's a limited. All of these are true. On top of whatever you guys said, is you cannot go beyond. I guess this is something Matthew was referring to as well. You cannot go beyond the chemical energy level per unit mass of the fuel in the chemical propulsion. So on top of whatever limitations we have discussed before, there's also this issue that you can't really go higher than a level of thrust. So, and you also, if you run out of thrust, you run out of fuel. So to address this problem, we have introduced, and we're going to talk about three main alternative propulsion systems: electrical rocket engines in general. And whenever I say electrical rocket engines, I mean that we are going to use electric field or electric charge or like electric power in a way to generate thrust, right? It is not just electric and magnetic field. And nuclear rocket engines, solar rocket engines, essentially are going to use nuclear and solar energy as their main mechanism to generate thrust. There's a small comparison here we have between the specific impulses of chemical rocket with the rest of these. You can see, for example, like a specific impulse of a chemical rocket is usually in range of 170 seconds to 465 seconds. The thrust duration is usually in minutes, 465 seconds. Yeah. But if you go to nuclear propulsion systems, your specific impulse or electrostatic propulsion system, which has the highest, your specific impulse is going to range from 2,000 to 100,000 seconds. So the trust duration will be a matter of months or even years, right? That's a very, very different approach to rockets, right? Okay, so, but to be able, I'm not going to talk about electric propulsion in general now, right? To understand electric propulsion, we need to understand the basics of electric field analysis and magnetic field analysis. So, the first thing you have to know is the Coulomb's law, right? What does the Coulomb's law tell us? Who remembers? Or do we know what Coulomb's law is? Have you heard the word before?
Yes.
Okay. No? So, right. So those of you who have, who can tell me what the Coulomb law says? I mean, it essentially says there is a force that exists between two charged particles, right? Or like more than one charged particle, right? But how do we find that force? What is the relationship that is going to help us find the electrical force between two charged particles? Does anyone, those of you who said you do remember what the Coulomb's law is, who remembers the equation? Yes.
I don't remember the equation, but I remember it has something to do with the radius of the particles between and the distance between.
The distance between the particles specifically, right? The radius of the particles, the distance is usually much greater than the radius. So Coulomb's law, the electric force, the electrostatic force between two charged particles is equal to a constant K multiplied by charge of particle 1, Q1, the amount of charge in particle 1, multiplied by charge of the particle in charge of the particle 2 divided by the distance between the two particles cubed multiplied. This is a vector equation, so this is a vector form, right? This is K Q1 Q2 divided by the magnitude of the distance to the part cubed multiplied by the vector distance, right? But for our use, these two simplify because we only are going to look at the scalar force between the two for our analysis. So the Coulomb's law is going to simplify to K Q1 Q2 divided by R squared. What does this remind you of? Yes.
Gravitation.
Newton's gravitation. What was the Newton's gravitational law?
G I wanted to over R.
R squared,
Yeah.
right? It's essentially that is also a vector form of the equation. So to be correct, you have to write it like this, right? The vector form. So these two laws are analogous, right? Charge of the particle versus mass of the mass of the planet. But how do we find the constant K? It is 1 divided by 4 multiplied by the permittivity of the free space, right? We know the permittivity of free space. Based on that, we can calculate this K to be 9 times 10 to the power 9 newtons meters squared divided by coulombs squared. Okay. Electrical permittivity, that the epsilon is the ability of a medium to store charge, or the ability to store charge in free space, in a space. And its units are coulombs per volt meter. We can calculate the permittivity of any other medium using this equation. The free space permittivity multiplied by the relative permittivity. That does depend on your specific medium. Okay, an electric field in this scenario for a charged particle is going to be calculated by an equation that is similar to the force equation. So electric field is defined as, it can be calculated as K multiplied by charge of a particle divided by the radius cubed multiplied by R. So what does this says is that any charged particle creates an electric field around it. The strength of that field is related to the distance that you have from this charged particle R and the charge of the particle, and also K, which is a constant. Okay, so I assume these are things that you have. I guess one of you had not seen the Coulomb's law, but the rest of you, I assume these are the things you have seen. But if that is not the case, please make sure to ask questions. Okay, so based on these two definitions, based on the force definition and the electric field definition, what is the relationship between electric field and force? So essentially what I'm asking is, let's say you have two charged particles, Q1 and Q2. What is the force that Q1 exerts on Q2 as a function of the electric field that is generated by Q1? What do you think it is? You want a bonus? Yes.
It would just be E times Q2.
That's it, yeah. And yeah, thank you. You will receive a bonus. Also, I guess all you wanted to give me the same answer, right?
Yeah.
Okay, so both of you just send me an email to receive the bonus. Exactly. So the idea is if you place a charged particle in an electrostatic field, in an electric field in general, the force that is exerted on that charged particle is going to be equal to electric field, a strength of the electric field multiplied by the charge of the particle. Okay, so how can we use this to our benefit? So almost if you're interested, we are not interested in electric field or charge particle. We are interested in generating thrust, right? So how can we use this to our benefit?
You just apply a force on some mass and throw it out the back like thrust.
You essentially create an electric field, right? And you make sure that you pass some charged particles through it, right? So essentially you have to spray some charged particles into your system that has an electric field, and that electric field is going to exert some force to it and accelerate it. That's the idea, right? That acceleration is the thing that is going to give us the thrust that we want. Okay. But the idea is also we know that if a charged particle is moving in an electrostatic field, there will be a magnetic force. There will be a magnetic field creation. There will be a magnetic force that is exerted on that charged particle as well. That magnetic force is calculated as Q multiplied, this is the charge of that specific particle, multiplied by the velocity of that particle, charged particle, cross magnetic field B. Okay. Have you seen these equations before for the magnetic field? No. What do you read in your, what do you study in your electrical engineering for non-majors?
Copy code from slides.
You really don't. It's just not loud. You
So
just
they-
use the code, that's all.
Well, what are you doing with MATLAB? What is it that you're analyzing?
Very
Like power
basic.
from a resistor or like phase
Very
angle.
basic DC circuits.
Oh, just circuits.
Yeah.
A little
It's-
bit of
yeah.
AC and a little bit of three-phase.
That is very useless to you guys.
Yeah.
Exactly.
Yeah. This is something you want to mention in your senior exit survey next semester, right? Those of you who are seniors. Those of you who are not seniors, 2 years later, right? Like a year and a half later. You definitely want to bring this up. Okay. So B is a magnetic field. The units of magnetic field is Tesla, Webers per meter squared. And the idea, we also have to make sure that we understand that there is a cross product here. So if the movement of your charged particle is in the same direction of the magnetic field, there won't be any force. The magnetic force is going to be 0. Okay? So again, magnetic force is equal to charged particle multiplied by the velocity of the charged particle cross the magnetic field. Right. Questions? Do we have any questions? Are we confused at all?
What's the unit for Tesla?
That's the unit for magnetic field.
Oh, like what? Like
Weber per meter squared.
what's Weber?
It's a unit.
Okay.
Okay. We can find the magnetic field. Let me go ahead. So magnetic field can be found using the permeability multiplied by the auxiliary magnetic field H. And that permeability for any medium is the free space permeability multiplied by the relative permeability. Free space permeability is a function of the speed of light in vacuum multiplied by the permittivity of vacuum. Like whenever we say free space, we mean vacuum. Like the source that I use uses free space instead of vacuum for some reason. Okay, so we understand how to calculate these forces, the electrostatic forces, or the electric force and the electric field force and the magnetic field force. But how do they change the momentum equation? Is there anyone who can tell me? Yes. Go ahead. I thought you don't want to say anything? What do you think? What is it? Bonus. There is bonus involved, but I guess he got it. Yes, go ahead.
You would just be having to add the electromagnetic and magnetic forces to
As forces, right? What was the momentum equation? Essentially, the Newton's second law. Sigma F is equal to total derivative of momentum. Right? Okay. So this part of it is not going to change, but this part of it is essentially instead of having the pressure forces on all of those other forces, we're going to have magnetic force plus the electrostatic or electric force, electrostatic and electromagnetic force. Okay. So the total forces are going to be Q multiplied by the electric field plus the velocity of that charged particle across the magnetic field, right? And then here, we essentially have assumed that m of the charged particle is constant, which makes a lot of sense. Like that a specific particle is not losing any mass. Its mass doesn't really change. And we have written the new momentum equation. Like mdv/dt, this is for each particle, okay? But the point is, here, we are looking at one particle. There is another force involved, which is, you can see right here, that we need to account for. What do you think this force says? What are we missing? We have a couple of charged particles, like we're looking at one of them, right? That is moving in a field that has some electric field and magnetic field, right? Because of the movement of the charged particle in the electric field, right? We essentially have two magnets, right? There's a charged particle moving like within this magnetic field. Because of this movement, we have an electrostatic force QE, and we have another force VQ, like Q, VQ cross B. Well, here in the momentum equation, we have added a third force. What is this third? This is the momentum equation for one charged particle. What is this extra force? This the force. Since you are not very familiar with these topics, all of my questions have bonus points if you give me the correct answer. And I want all of you to try to give an answer. Yes, yes. Who had their hands up first? Keelan go first, and then all, and then what was it? Andrew? Andrew.
Is it some sort of like inertial force? Internal inertial force of the particle?
Internal of a particle? But it's already moving, right?
Yeah.
I guess no. It is not an inertial force. No. Yes.
it the pretty much the force time, or the not force, the mass times the velocity of the exit, because you're accelerating the mass of the particle, or you're accelerating the particle, so you have a force caused by the m dot v essentially.
No.
Okay.
But we need to account for that force as well. So we need to add that thrust force later. Yes.
So this equation accounts for just one particle with that at the end?
Just we are looking at one particle.
With that,
That's what I means. That I is a counter for all of the particles. It goes from 0 to like infinite number of particles you have.
Would it be like a force of attraction from other particles, like external?
You're very close. Exactly. So if you're looking at the particle and we are in a field with a lot of charged particles, we need to account for the collision of these particles, right? So this is the force of collision, right? Because the collision of charged particles can change the direction. And we're going to talk about this later. This specific force can actually have a huge impact on the total thrust output of your system. So you have to make sure you account. You essentially want to remove this. We want to reduce the density as much as we can, so we avoid any collisions that are happening. Okay, does that make sense? Okay, so and I guess this should have been here. This is what essentially what the whole thing is, right? The idea is you have an ionized gas that is passing through an electric field, electric and magnetic field, and you have the direction. We know the direction of electric field. We know the direction of magnetic field, which is always perpendicular to the electric field. This is the direction of magnetic force on your ionized gas. Why does it say plasma here? What is plasma?
Just like a stream of like condensed electrons.
No.
It's just a very excited gas.
I mean, it is excited, but we don't call it plasma because its molecules are at this excited states. See, I guess you can gather a plasma is an ionized gas, right? I'm sure there are a lot of excitation here as well, but the ionization is the part. So whenever you see the word plasma, we're talking about a gas that is ionized. And we're going to talk about the ionization process. And this is actually the whole general idea is an interesting topic. If you are interested in doing research on plasma, Dr. Farooq used to do some plasma research. I'm not sure if he still does, but he used to do some plasma research. I also used to do some plasma research. Yes. Okay. So we can just look at these two forces separately. If you look at the electric field alone, the rate of change of velocity is going to be the charge of each particle divided by the mass of the particle multiplied by the electric field. But because of the direction of the magnetic field, we can actually, the velocity that is here due to magnetic field is very similar to the centrifugal acceleration, right? How did we calculate the centrifugal acceleration? V squared over R. So it's the same idea here. V squared over R of G should be equal to a magnetic force divided by mass of the particle. Okay. Well, what is this R? So, like in a rotating body, we know that R is either the curvature, like if you're in a fluid, the curvature of your streamline, or just the radius of a disk or whatever, right? We know that R is radius. But here, we're talking about charged particles, and what I'm saying is your magnetic force is going to be equal to the velocity of that particle divided by a radius. What do you think this radius is? I don't really expect you to know this, but yeah.
Is it the distance from the center of the gravitational field?
No.
Or not center of gravitational field?
No. No. And this, yes.
The distance between the nucleus and the electron cloud? Or like the
No.
atom point?
No. sounds very quantum mechanics. Who can tell me? You will get more than 1 bonus point for this answer. I'm going to give you like a couple of minutes to think about it. What is that R? Do we all know what the question is?
Can you repeat it again?
Sure. Okay, so I said if you want to look at the contributions of this electrostatic field and the electromagnetic field separately, this is the relationship between velocity and the electric field and the charge of the particle. This is the relationship between the velocity and the magnetic field specifically, right? This is essentially what we're saying is the magnetic field is working as a centrifugal force, right? That is the idea. But which essentially means that magnetic field divided by mass magnetic acceleration, let's call it magnetic acceleration, is going to be equal to the velocity of a particle squared divided by a radius, right? But like in case of the mechanical or aerospace, like mechanics, like physics, right? That radius is usually the curvature of a disk, or like in solid mechanics, it's a radius of a disk or whatnot, right? In fluid mechanics, the curvature of a streamline. Okay. What I'm asking is, what is this R in electromagnetic? Yes.
Is it the radius of the gyration itself?
What is the radius of the gyration?
I thought it was R right there.
Well, what is it? What do you mean by radius of
It
gyration?
goes through a path and it gyrates and it creates a disk. You said the radius of that disk.
Yes, yes. It is called the radius of gyration. And your explanation was not complete, but you are close. The idea is these two forces are not necessarily in the same direction, meaning that when your particle is moving, there will be some like movement. As it moves, there will be like it will have a spiral movement, something like that, right? And that will have a radius. That radius of gyration is the radius of that spiral movement. Okay. Does that make sense? Do we have any questions? No. Okay. I guess we can also have a frequency of gyration or the angular velocity of gyration. And because of this gyration specifically, we are going to have a velocity component called the drift velocity. That is your electric field cross the magnetic field divided by magnetic field squared. And we of course want to minimize this. Right? This is not a good thing for us. Okay. I guess we did talk about this. Let's move on. So how does let's come back to this later when we're talking about electrostatic. So the working principle of a electrostatic or electromagnetic propulsion is you put a charged particle in a magnetic field or electric field and you accelerate it to generate thrust. But that is not the only way we use electrical power to create an alternative mode of propulsion. The other way, which is I guess a little more familiar to aerospace and mechanical engineers, to people who deal with energy, right, is electrothermal propulsion. And the example we have is the different types of resistor jets, which you are going to simulate, like one of these, for your own project. What is electrothermal propulsion? Essentially, what it is you heat up your gas and accelerate it, but you don't use combustion to heat up your gas. You use a different method. What is the method? You put an electrical heating element in our heating chamber, not a combustion chamber anymore. It will heat up the gas and it will accelerate the flow. It will generate thrust. Where does the electrical power come into play? These are all electrical heaters. That's the idea. Yes.
What's with the transverse coiled wire? Like the rest of those designs I could see making sense. I don't get the transverse coiled wire, like why you do that.
You can add, like with this mechanism, you can, we'll talk about this is the specific problem that might arise because of this, but also the benefit of it. With this specific mechanism, you can actually heat up your gas more. Why? Because there's a lot of pressure drop happening here, which means that your residence time, your gas's residence time, here is going to be more, so you have more time for the energy transfer to your gas. Okay, so now let's talk about the electrothermal propulsion. We are going to talk about the efficiency of electrothermal propulsion, and then we are going to go back to electrostatic propulsion and electromagnetic propulsion, and so on and so forth. Okay. And they usually they're operating. The heating element's operating power is between 1 watt to 100 kilowatts. So this is the information you want to use when you are working on your project. The heating element's power should be between 1 watt to 100 kilowatts. I usually give you the option. Okay, so the problem with this type of rocket, with this type of propulsion systems is the energy loss. Like the whole working principle is based on you heating up gas, and you are flying. These are very small systems in general. You are flying in space, right? And what will be the problem with flying these in space? That's maybe a question. The working principle of these is you heat up some gas, and it will accelerate the gas, and you will get thrust. But you are flying in space. Yes, I guess the three of you. Let's go with Andrew first. We're going to go to Madden and Matthew. Andrew.
So unlike on Earth, you have to carry your own gas as fuel because there's no gas in space.
That is always given with rockets, right? You have to carry your own propellant, so that is not an issue, specifically with this type of propulsion. Madden. Matthew.
I was just gonna say, like, you get a lot of radiative heat transfer, which is gonna cause thermal loss into space.
Exactly. So the losses in a space are going to be extensive, right? Because the heat transfer that you have is between some temperature and 0 Kelvin, right? The radiative heat transfer is between. This is a lot of energy loss to a space. There's a lot of cooling. So we have to make sure we account for this cooling. We have proper, I guess, what we call radiation shielding in place. This is heat transfer radiation shielding, specifically in place to reduce the radiated heat transfer. Does this make sense? Yes.
Do the heaters ever get to a point where they can ionize the gas? Or...
That is a good question. So to ionize the gas, like 6,000 Kelvin. I guess it is possible. I never thought about it, and this is not my area of expertise. So I need to look this up. But it is technically possible. You also have to think about. Okay, I guess I have an answer for this. We are going to talk about it. No, let's talk about it right now. Okay, so there is a trade-off with these type of propulsion systems. So how do we calculate thrust? It's m.b multiplied by the velocity, right? The velocity is important, right? And if you heat up your gas more, you're going to get more acceleration at the end. That doesn't necessarily will give you give you more thrust, but it's generally a better thing to do. Like you heat up your gas more. But the problem with it is this: if you let the gas stay in the heater more and more, you are going to keep heating up your gas. At some point, your gas is going to be so hot that might melt your heating elements. So we usually don't get to the temperatures that might ionize our gas because of the structural limits of the heaters. Does it make sense? There's a trade-off. So you don't want your gas to be too hot, but you also want to heat up your gas. The whole principle is based on you heating up your gas, right? So I don't think we will ever get to that ionization thing that you mentioned. But that is a very good question. Why don't we do this? So I guess Keelan asked us question, why don't you do a little bit of research on the ionization problem, possible ionization problem, electrothermal propulsion, and then give us a 5-minute presentation next week, next Wednesday. Yes?
Isn't the theoretical limit for heating gas the speed Mach 1 using Rayleigh flow? So would that be limiting this exit velocity with ionized gas as well? With your using
So
Rayleigh
we
flow?
definitely, for electrothermal propulsion, for resistor in general, you're operating at velocities that are smaller than Mach 1. Usually, it's very difficult to speed up your gas with heating to velocities that are higher than Mach 1, which essentially means that you definitely need to include a convergent divergent nozzle. These are micro convergent divergent nozzles, meaning the throat area is very small, right? So the idea is the acceleration and deceleration is controlled by your convergent divergent nozzle, not the fan of flow or the Rayleigh flow.
But would ionization in this case increase the thrust? Like if theoretically you did reach that amount and you had ionized gas, would you be increasing the thrust at that point?
If you couple it with the external magnetic fields, yes.
Would that also be a possible solution for the overheating?
The overheating problem is a structural problem.
Yeah,
It is not
if
a...
the gas moving, would it be able to heat up enough?
No.
I guess at that point it wouldn't be.
Because if you are not in the heater anymore, you're not going to heat up, right? And if you are in the heater, you are limited by the melting point of the heater, which is, I guess, for most metals for the metals that we're going to use in this are going to be less than like 6,000 kelvins. Yes.
Unless you use a plasma heater where you could they use like arc lighters in a lot of jet engines. I think you could probably leverage that tech, so you could heat the gas way beyond what the lighter itself could handle.
Exactly, yeah. So the arc jets are the things that we are going to discuss after the electrothermal, after the resistor jets. Exactly. Okay, so let's see some equations. Reminder, we had a figure of merit called the characteristic velocity, which was your effective exhaust velocity divided by the thrust coefficient, right? Also equal to a specific impulse multiplied by the gravitational acceleration at the surface of the Earth divided by the thrust coefficient. We can come up with this formula for the characteristic velocity equal to the square root of gamma RT. These are things that we have seen. These are essentially just copy and paste from the previous slides. We can rewrite this to give a little bit more importance to the molecular weight of the gas. Okay? Essentially what we have done here, instead of using the specific gas constant right here, I've used the universal gas constant divided by the molecular weight. It's the same thing, right? Exactly the same thing. And then all of the gammas are gathered into this huge gamma, all of the ratio of specific heats. Okay, why do we need to do this? I guess we don't really need to do this, but we have to be aware of the fact that characteristic velocity of any rocket is a function of its molecular weight, a specific heat ratio, and the temperature of the propellant. Okay, So how important is the molecular weight in determining your characteristic velocity in a chemical rocket?
Very important. It's part of the momentum equation. It's just the mass. So the higher the mass, the faster you can get it. The more thrust.
The higher the mass flow rate, right? That is not the mass. So let me rephrase the question. Is temperature more important in a chemical rocket or the molecular weight in determining the characteristic velocity?
Temperature.
Because we have a huge temperature jump there, right? Because we have combustion, huge temperature increases, right? So essentially the composition of the gas is going to be more important. Like how good of a combustion you have, like what type of fuel you're using, all of these are going to be more important. But in an electrothermal rocket, temperature does, I guess we do that. It does, the molecular weight is going to become more and more important. You don't really have a combustion to offset the inverse effects of the molecular weight. Okay. Do you have any questions so far? No. Let's see. Okay. One important thing that we have to analyze to understand the effectiveness of an electrothermal propulsion system is calculating the kinetic power to thrust ratio. How do we calculate the kinetic power? This P of J is usually used for electrothermal propulsion systems, but you just can't say kinetic energy jump, right? It's exactly the same thing. How do we calculate the kinetic energy jump in the system? Like half of m dot, the exhaust velocity divided by to the squared, and that is divided by the thrust, which is m dot multiplied by the exhaust velocity. So power to thrust ratio is equals to half of exhaust velocity, or half of the specific impulse multiplied by the gravitational acceleration at the surface of the Earth. Another figure of merit here is the efficiency of the electrothermal propulsion. Okay. How do we calculate the efficiency of the electrothermal propulsion? The idea is not all of the electrical power in the system is converted to kinetic energy jump. So you just have to compare the kinetic energy jump, which is your kinetic energy at the exhaust minus the kinetic energy at the inlet. Don't have an inlet, it's a rocket, so just the kinetic energy at the exhaust divided by the power. So m dot V exhaust squared divided by 2 divided by your power. Okay. Since we are dealing with a heating element, how do we calculate the power of a heating element?
Resistance times voltage.
What is it?
Resistance times voltage.
The current multiplied
Current
by,
times voltage, sorry.
what did you say?
Current times voltage.
Current times, electrical current times voltage. Voltage, current. So here in this chapter, whenever you see this V without any subscript, that is referring to the voltage. If you see V0, that is also referring to initial voltage. Okay. And I is always current. So efficiency of an electrothermal rocket can be calculated using its thrust, a specific impulse gravitational acceleration divided by 2 multiplied voltage multiplied by the electrical current. Usually it varies between 65 and 90%, meaning that we can actually have very efficient systems. Like a 90% efficiency, thermal efficiency is huge. Let's have an example problem. We have a 1.7 kilowatt electrochemical rocket with helium as propellant to be designated and developed using tungsten filament resistive heating element for obtaining the thrust coefficient of 1.8. So, assuming the mass flow rate of the propellant is 0.12 grams per second. Determine the exit velocity, characteristics, velocity, the temperature of the propellant gas, thrust, and a specific impulse for electrochemical rockets with the thruster efficiency of 0.85. I'm going to give you a couple of minutes to solve this. But one thing you should look at in this specific example problem is the mass flow rate of the propellant. Mass flow rate of propellant is 0.12 grams per second. That is not even 1 gram per second. That is essentially 10% of a gram per second. It's nothing, right? So these propulsion mechanisms are very, very small. That's the idea. What is given to us?
Power, the efficiency, coefficient.
Power is given to us. It says a 1.7 kilowatt electrochemical rocket. So your power, that V multiplied by I, Pj, is given to you as 1.75 kilowatts, right? What is it?
You can substitute in previous formula and calculate exit velocity.
Yes, exactly. What was the previous formula? Efficiency of a electrothermal rocket. What was the equation for it? Without going back to your notes, tell you what the equation is.
Mass flow rate times exit velocity square over 2pg.
So what I wanted to hear was the definition of it, not the equation itself. Yes.
Changing kinetic energy over the power of the.
So essentially the amount of power of the element that is converted to the change in kinetic energy, right? Which is our goal here, right? So which is, as Angelica said, it's 1/2 mv squared divided by, or m dot v squared divided by pj. Do we have m dot? M dot of p, propellant.
0.12.
We have everything that we
0.12 grams per second. How do we convert this to SI? Times 10 to the power negative 3 kilograms per second. Right? What is the power? 1.775 kilowatts. What is eta?
25.
So what is the exhaust velocity?
4,979.
I don't really know if this is correct, but I trust you. 4,979. 4,979. That's meters per second. See, mass flow rate is very, very small, but the exhaust velocity is huge. So with that small of a, we can actually are generating enough thrust. That's the idea. Okay, what is the rest of it? Assuming the mass flow rate. Characteristic velocity. How do we calculate characteristic velocity? C star, yes.
The molecular weight. Yeah.
What is it?
What's the gamma of helium?
What is the gamma of helium? I don't really recall. I have to look up that. But we don't need the gamma for the for this. Just we can just divide everything, the exhaust velocity, with ACF, and that will give you the final answer. So one thing you have to keep in mind is that whenever we're dealing with rockets, we introduce this idea of effective exhaust velocity, right? And here we are always referring to thrust as m dot of p multiplied by effective exhaust velocity. So we are not including the pressure area that exists. Does make sense because our density is actually too low, right? So this exhaust velocity and effective exhaust velocity are the same thing. That is the idea. So this is how we calculate the characteristic velocity, and then for the gamma of helium is 1.66. The rest of it's a plug and try. We find the total temperature at 2 and the rest of the calculations. Do you have any questions? I don't want to go further than here, but we still have a lot of time, so let's go further. Let's see, before going further, do we have any question about the material of this part of the lecture? Everything's crystal clear, right? So, that some of you, I guess it was Keelan and Matthew, did bring up that you talk about the limitations of the resistor just in general, and we are limited by the structure of the melting point of the heater, essentially. What can we do to create or to remove that limitation? We can use an arc instead of a heating element. So instead of a heating element, we are going to create an arc that is going to reach much higher temperature, that is going to change the gas, increase the gas temperature to a much higher temperature. This is where you will definitely see some ionization, right? And this ionization we can use by adding a cathode and an anode to a system to our benefit. So an arc jet is essentially an electrothermal propulsion mechanism plus an electrostatic electromagnetic propulsion mechanism. So the arc that is present here is responsible for heating of the gas as well as the ionization. Okay? You don't really need to do any calculations with this. We just have to know what it is. Questions? Yes.
It looks like it has no convergence before the arc. Is there a reason for that? After the arc, sorry.
Right here.
No convergence after the arc.
So what Keelan is saying is that why don't we have a converging diverging nozzle? First of all, this is the schematics, right? It doesn't really mean that we don't have a converging diverging nozzle. In a lot of cases, though, especially in the alternative modes of propulsion, in a lot of cases we don't have a converging diverging nozzle, or we only have a diverging part, because you can design for it. You can actually make sure that at that point you are at the Mark 1 criteria. So you just add the divergent nozzle. Right? Think about it this way. We are dealing with charged particles anymore that can be accelerated using magnets. So instead of the divergent or convergent part of the nozzle, if you are in a subsonic flow regime, you can effectively build a converging part of the nozzle by using magnets, right? Okay. Let's talk about electrostatic propulsion. Using the electrostatic propulsion, we can actually increase the impulse of the thrusters beyond the limits of electrothermal thrusters, because we are going to take advantage of the fact that the gas is going to ionize. So essentially, we are going to accelerate the non-neutral charged particles in the system, so the exhaust gas is going to be, I guess, a little more faster. So force the thrust force that we are generating here is a function of the strength of the electric field, the charged particle, and their direction. Okay? In general, we prefer to work with positive ions compared to electrons. Why?
I imagine they have more mass, which just makes it better for propulsion.
Exactly. Due to the heavy, electrons, like ions, are much heavier than the electrons, like free electrons that are just flying around. So it is easier to accelerate them. Mass flow rate, all of those, everything essentially whatnot is going to be more beneficial to that. Okay, so.
I have a question. But does it mean by the same logic that we should use like big molecules and convert them to positive ions? So the bigger molecule, they have higher mass.
That is true. Yeah, we should definitely. So that logic does apply here, but there is also a compromise when you when you use heavier and heavier molecules in general, right? What do you think that compromise is?
I think it's harder to accelerate them.
It will get harder to accelerate, right? The point is, the focus of your design should be on accelerating the ions, not the electrons. Like the choice of gas, we're going to talk about the choice of gas later on, but they usually use xenon for this. Okay, so essentially, the working process is you have to ionize the gas first, and then you just have to pass it through an electric magnetic field to make sure that you have a very high bulk velocity. But there is one problem that we have to make sure that we stay away from, and that is having too many ions in the exhaust of the system, right? Why? Because too many ions. Go ahead.
I was just gonna say, because then you start getting the collision effect.
You are going to start getting the collision effect. So you have to make sure you include this in your analysis. You have to know where the limit is. You're going to see throughout this process that designing an alternative propulsion mechanism in general requires a lot of things to be aware of, to account for. Essentially, there are a lot of things that you have to account for. Okay, how do we create these positive ions? Let's say, and this is a plasma generation system in general. It's an ionized gas generation system. You have to have a cathode and an anode, and there should be an electric potential between these two. You pass a gas through this cathode and anode, and it will break the gas down, right? What does breakdown mean? Ionization. It will help you ionize the gas. But for each gas, the electric potential that you have to apply between the cathode and anode is different. So you have to make sure, let's see if we have, I did have the numbers for different gases. You have to make sure that you are applying that minimum electric potential between the cathode and anode. Yes?
But if you end up, where do you find energy to make this difference in potential between anode and cathode? It's not like you can just plug into the power outlet and get that energy out. Should you have big batteries then?
Sure. I mean, it doesn't need to be a big battery, but it needs to be a power source that is going to generate the amount of potential that you want to generate.
But that's the increase mass.
You also create rockets with huge amounts of oxidizer fuel. That is a design. It requires the electric potential. You have to provide electric potential. Did you want to add something?
Oh, I was just gonna say solar RTEs.
You can also use solar cells. Yes. For these. Okay. So let's look at an electrostatic propulsion mechanism. It has three main components: the ionization chamber, which is right here. The whole thing is an ionization chamber. We also have an accelerating chamber, which is this small molecule right here. I guess that all of these can also accelerate your ionized gas. And we also have a neutralizing electron gun. Okay. So this part of it is your ionization chamber. I mean, the ionization chamber is technically just this part, then you have cathode and anode. But throughout the process, you will see ionization in general. The ionization chamber has a cathode and anode. We can have auxiliary modes of ionization in this process as well. Because of the ionization, because of the electric potential that you're applying there, your cathode is going to heat up. That heating of the cathode is going to augment the ionization itself. This is essentially that it's going to emit electrons and augment the ionization. This is called a thermionic emitter, right? So the heating of the cathode is actually a beneficial thing to us. Okay, so the discretes are very important in designing an electrostatic propulsion mechanism. As you can see, we have two sets of grids. One is charged positively, the other one is charged negatively. These are responsible for accelerating your ions in general. Okay, but there is a problem. Let's see. There is a problem with the extensive use of these grids. What do you think this problem is? Let me actually go back.
They get bombarded by heavy particles and get out of the very fast.
They get they're always bombarded by ions, right? And what is the problem with the ion bombardments?
That just oxidize any kind of metal. Rather
It
than
will. Yes, did you?
I was going to say it slowly loses its charge.
If it slowly loses charge, the oxidation problem, the corrosion problem is going to be I guess a bigger thing because you can account for the deionization. You always have permanent magnets. You can think of something, right, to make sure it doesn't lose its charge. But the material you use here is going to be very important because you are constantly bombarded by the ions, right? And there will be some sputtering, there will be some deposition of the gas onto your system, which will result in the erosion and the destruction of this grid. So we have to choose our material carefully. The material that is usually used here is molybdenum, which has a very low sputter characteristic. So you won't really see any deposition through sputtering on the grids.
But since they are charged, can you just add magnets to correct trajectories so that you control them and they don't bombard randomly?
These are in charge of doing the exact same thing that you said. Yes.
Out of curiosity, so like, do you just use a really heavy metal because, like, are heavy metals just inherently more corrosion resistant? I imagine they're just harder to ionize.
I don't know. That you have to ask that from a material scientist. I am a computational fluid dynamicist, so I have no material knowledge whatsoever, zero. Okay, so the exhaust velocity using all of these mechanisms is going to lead to exhaust velocity that is between 3,000 and 60,000 meters per second. A really huge exhaust velocity, but they are not going to generate a huge thrust. Why? Because the mass flow rate of the propellant is very small. Just like the electrothermal mechanism, that the mass flow rate of the propellant there was only 0.12 grams per second. The last stop is the neutralizing gun. So essentially, you ionize your gas, you accelerate it even more, then you neutralize the ions. Then you have generated the thrust. Why? Why do we even care? Why do we need to neutralize the ions? We don't cool down the exhaust of a chemical rocket. Why do we have to neutralize the ions? Yes.
Are they just going to get attracted back to the magnet if we don't? So like, they get pulled backwards and that kind of
And that they're not going to get attracted back, but you are going to create an ionized area around your propulsion mechanism that might cause issues, right, with your whole system. And we don't want that to happen. That's why we have to include a neutralizing gun in our system.
So it's basically to protect the inside electronics.
Yes, yes, that's, yeah, exactly. Okay. Where is the nozzle? I guess we did talk about it a little bit. In electrostatic propulsion, we don't have a nozzle. Why?
I imagine.
What? No, that was my mistake.
I imagine.
He had his hand on his face. I thought he's
density is.
you.
I imagine the density is like way too low to even get any kind of choking effect. So you just try to keep the flow parallel to max.
So Matthew is actually bringing up a very interesting fact. It is not that we don't need to use the nozzles, convection diversion nozzles. In some scenarios, we can't use convection diversion nozzles because the density is too low for the convection diversion nozzle to be even remotely effective. That is a very interesting thing as well. Yes.
Because the purpose of the convergent divergent nozzle is to speed up the flow, or speed up the velocity, and because you have the magnets doing it for you.
We have the grid specifically and the magnets doing that for us. So we can actually design to remove the necessity of the convection divergent nozzle. Let's just stop here. We're going to talk about a lot of equations. So let's just stop here. I think we're going to be done with the material for the course on Monday, which was the goal, right? No, we want it to be done by Wednesday. We're going to spend Wednesday talking about the, what is it? Project, I want to say. On Monday, we're going to do practice problems. Exam is on Wednesday, right? Not next Wednesday.
Everybody's